Good afternoon, everyone. So I'm going to take over from Goran here to talk a bit about the potential applications for silicon photonics and other integrated photonics applications in space optics. And this is going to be quite a different talk to Goran's, because it's more of a kind of speculative look at what the future applications could be, and I'm trying to do it as a little bit of an introduction to what's going on in space optics for those coming from the world of integrated photonics. So my main question is, can silicon photonics be useful for space systems? You'll all be aware that in the last several years, in the last decade or so, there's been a real explosion in the number of satellites that are in space that's been allowed by much cheaper satellite launch costs. So companies like SpaceX coming into the industry and allowing people to launch satellites for much less money. And so there are many more satellites available, and many of them already use optics for some of their key functions. So some of the applications I'll look at, some of the functionalities I'll look at, are related to free space optical communications, inter-satellite optical interconnects, RF over fiber systems, and I'll touch a little bit about things like remote sensing and planetary exploration. Now, the first one I'll look at is free space optical communications. When I say free space optical communications in this context, I mean laser communications between satellites and between satellites and the Earth. And so there are lots of this figure on the right from the Dutch organization TNO sketches out some of the different kinds of systems that we'd want to have laser communications between. So we have communications between satellites in low Earth orbit. So these could be constellations of satellites in the O. These could be small CubeSats, communications down to the ground, communications from deep space back to Earth, and then communications around the moon and then back to Earth. Now, at the moment, most of these kinds of communication systems are handled by RF links, but free space optics has many potential benefits over RF for communication systems. You can reach higher data rates with optics. Optical systems have lower size, weight, and power. You can have a lower cost per bit, so the system itself is cheaper. One important one is that the RF spectrum is heavily regulated. So companies wanting to use RF spectrum need to buy parts of the spectrum for use, whereas for laser optics communications, it's not regulated yet. And the communications are fundamentally more secure because the laser beam is much more focused than a transmitted RF beam. So you're illuminating a much smaller area. So free space optics is going to be needed partly to be able to transmit much higher data volumes that can be transmitted already. So this could be things like transmitting data from remote sensing satellites that are looking down at Earth. So some of them have hyperspectral images that create a huge amount of data, and we want to get all that data back down to ground. It can be needed for quantum key distribution, and they could also be needed for communications with remote areas. Now, where are we really today? Like, is this kind of communication system a reality, or is it happening? The first satellite laser communications demos happened in the 2000s. And so there was this slide shows the Space Data Highway, which is an European Space Agency and Airbus very small optical communications constellation that was set up and has been operating since 2016. And so this constellation is set up, it's essentially two satellites that are in geostationary orbit, and they're used to provide a data backbone so that satellites in low Earth orbit that are observing the Earth are able to send data back to their ground stations at very high data rates, even if they don't have line of sight to the ground stations. So the communication will happen from the low Earth orbit up to geostationary orbit, and then down to the ground station where they want to transmit the data to. And so this link operates at 1.8 gigabits per second, and it's been operating continuously in that time. So laser optics communications links are a real practical reality already. This is another example of a free space optical system. So there's a German company called TSAT that's already selling commercially a variety of different sized satellite optical communication terminals. And so some of them are designed to communicate in the LEO layer, some are higher orbits at GEO, some are communicating down to Earth. And so they have different sized terminals which can transmit at higher or lower powers depending on the distance and data rate over which they need to transmit. So this picture on the right shows one example of one of their terminals. So this is a TSAT SCOT 20 small sat optical communications terminal. You can see the size of it compared to a €2 coin for reference. It weighs around 1.6 kilograms, and it can do 100 megabits per second data communications between two satellites in a LEO orbit. So they've already deployed 56 terminals in space. They have 180 more in production. So this is already essentially an off-the-shelf commercial solution for companies wanting to deploy optical communications terminals. Now, what actually goes into one of these communication terminals on the right? You'd have devices like a light source. It could be a laser, it could be a detector for the receiver side. There would be modulators for encoding the data, amplifiers for increasing the power to have a strong enough beam to actually reach the other satellite. And then you'd have, and those components would often be connected by optical fibers, and then there'd be a free space element to that system. So you would have a tip tilt mirror, which is able to control the angle at which the laser beam is transmitted away from the terminal at, so that you can point the beam at the target. And you also have any optical components that you need to be able to focus, to create a beam that will be focused enough at a long distance. So that looks like a little bit like a small telescope. So these are, at the moment, mostly some combination of bulk optics and fiberized optics systems. You also need feeder links. So it's not enough to be able to just communicate between satellites that are in space. You also want to be able to communicate down towards ground. So what does that look like in practice? Well, you have your laser communications terminal, and then you also have an optical ground station. And it looks essentially like a small observatory that has something looking a little bit like a telescope. And so these ground stations, they handle things like setting up beacon for initializing the beam pointing, kind of creating a handshake between the ground station and the satellite. They then handle things like pointing, acquisition, and tracking, so that it stays pointing at the satellite as the satellite moves through the sky. And they also handle things like compensating for atmospheric turbulence. So they may have adaptive optics systems built into these ground station optics. So Kai Labs is a company that is already commercially selling these optical ground stations to customers who want them. And NASA last year showed that they could make a 200 gigabits per second downlink between their T-Bird system and a ground station on Earth. So this is all already kind of a practical reality which is happening. And at the moment, these systems are made of free space and fiberized components, but you can imagine that in many situations, these systems would benefit from reduced size and weight, would benefit greatly from being integrated on photonic integrated circuits. And this could just be that you integrate one small part of a larger system for communication onto a PIC and keep some of the other components that you can't really do in an integrated fashion yet. But it would reduce the size and weight, which is essential for satellites, particularly when launch costs are so high. Kind of every kilogram that you launch into space is obviously extremely expensive. You can get things like optical electronic integration that gives you things like reduced power consumption. The cost can be lower because you can make these things in high volumes. And fundamentally, photonic integrated circuits are robust. There aren't any moving parts. There aren't as many connections between different things. But there are challenges there as well. Existing silicon photonic devices may need to be re-optimized for space performance requirements, and you also need to think about qualifying them for space missions. There are devices available in silicon photonics already that you could see would quite quickly should be able to be quite quickly applied in space optic systems. This slide just shows one of the examples from our group, from the work led by Graham Reed and Dave Thompson on making silicon modulator with world record on-off keying data transmission rates, which has a silicon photonic modulator that also has a CMOS driver that's been integrated with it to create a module with very low power consumption. So that was a device that was made in the Cornerstone foundry. Another way that we're looking at trying to introduce an integrated photonics into this free space optical link is by trying to make silicon photonic chips for beam steering to replace the kind of tip tilt mirrors that are currently used in free space optical systems. So you'd have this kind of tip tilt mirror. This one is made by CEDRAT Technologies, and so these things weigh at least tens of grams, possibly hundreds of grams, and they are essentially just mirrors that are mechanically steering to different angles to be able to point at other satellites. And in our group's previous work, so work led by Dave Thompson and Graham Reed, they developed with a company, Point Cloud, 8x8. Well, they've developed beam steering chips which use silicon photonics to switch light between an array of 64 different grating couplers. And this image up on the top right shows that the output grating can be controlled by this switching array. And so if we then place a lens in front of this array of grating couplers, we can actually control what the angle which the chip is, the light beam is leaving the chip at. And so we have a funded project by the UK Space Agency where we're currently looking at trying to apply this same kind of system for free space optical communications beam steering. And there the main aim is to be able to handle higher optical powers than you can with current silicon chips. Now, sorry for the slide, it's a little bit of a wall of text. Away from the free space optical kinds of communication applications, there are many places within a satellite where you would want to use optics to augment the existing functions. So this may be to make high-speed, short-reach optical interconnects of the digital links, so making high-speed, low-power digital links in exactly the same kind of functionality that silicon photonics is already used for in data centers. But you may also want to try to augment RF communication systems. Today, most communications between satellites is performed by RF systems, and that's going to continue to be true in future. But RF systems can be improved by introducing optics in there. So you could use RF over fiber links between antenna arrays and onboard processors. You could look at doing RF frequency conversion using photonic microwave mixer subsystems, and that would give you much better spectral agility so that you can choose what frequency, what microwave frequency you want the system to work out. And the benefit there is that photonic systems can outperform electronics both in bandwidth and linearity. Microwave signals, the switching of microwave signals using silicon photonic or integrated photonic switches would also be useful for making reconfigurable microwave systems. And their photonics offers much faster response times and immunity, much better immunity to EM interference compared to electrical systems. And finally, photonics can be used to improve RF beamforming. So photonics could be used to implement optical true time delay lines that can make time delays in the RF domain. And so this would allow RF phased arrays to do beamforming and steering with the same kinds of advantages compared to electronics as in the other cases. Now, when we're looking, as we're looking to these various space applications, a good question is which kind of photonic integrated circuit platforms are going to be used, which ones are going to win out? And the answer is at this stage that I don't think anyone really knows. It depends heavily on the use case. It seems like things like SOI, silicon nitride, indium phosphide, and thin film lithium niobate all have their benefits and advantages. So you might want to use an indium phosphide based platform where integrated sources and amplifiers are essential, but you might want to use silicon and insulator if you're happy with an external laser, but you need very high integration density and some active devices. Or you might use silicon nitride if you only need passive circuits, but you also need to handle high optical powers. One thing to note is that chip volumes are unlikely to be very high in the short to medium term. So while there are many hundreds or even thousands of satellites going up into space in these years, that's still much lower volumes than you'd get, for example, in the data center space for telecoms. So the scalability of manufacturing is unlikely to in itself be a driver that chooses which PIC platform you want to use. But on the other hand, the maturity of integrated photonics platforms will help to lower development costs of new PICs for space applications. One essential question that hasn't really been answered yet is, can silicon photonic circuits withstand radiation in space? In space, there are different kinds of radiation that you'd encounter with different types dominating in different kinds of orbits. So you get cosmic rays of electromagnetic wave packets, so things like X-rays and gamma rays, and you also get radiation particles. So there are protons, electrons, alpha particles, and heavy ions that can all interact with and damage your system. And the kinds of damage that each of these particles create on the PIC is dependent on material. I just want to highlight one really interesting experiment. Was this mission, so this was just published this year, where a batch of silicon photonic chips were sent up onto the International Space Station and kept there for a year. And then they were brought back down to Earth, and their performance was measured compared to reference chips that were kept on Earth the whole time. And there were a number of radiation effects noted. The carrier lifetime of the silicon material was reduced. The passive losses of the waveguides were mostly unchanged. The losses of PN junctions increased a lot. And there were the occasional random increases, localized increases of optical loss, which is likely from very occasional heavy ions from space interacting with the chips. And the carrier mobility of the waveguides was unchanged. Now, interestingly, some of these results differ from ground-based X-ray and gamma ray experiments. And so we're getting from, so in the last couple of years that there have been some publications looking in practice at the radiation effects on silicon photonic PICs, but it's still early stage, and the kind of first signs are that silicon photonic chips can survive, but the performance of some devices is going to be altered but not completely ruined. But the more research and space qualification is going to be needed so that we can understand how we can design silicon PICs that can be more resistant to radiation. And so I'll just finish on this slide. What are some other applications where silicon photonics could be used in the future? You could imagine that spectrometers would be exciting for environmental science and for planetary exploration. So the kind of mid-hour spectrometers that Garan was talking about, they could be put on things like planetary rovers for exploration so that we can do spectroscopy on gases on other planets. You could use biosensors for monitoring astronauts' health. LiDAR systems would be useful in space, both for remote Earth observation, but also for improving things like docking between space vehicles, beam combination, navigation, position, timing. They're all kind of things in space where integrated photonics may be able to help in future. Okay. So that's all from me. Thank you.